Hello, everyone. In this video, we're going to talk about the end behavior of functions. And this is just picking up from the last video that I posted about limits at infinity. And that is what end behavior refers to. It's just asking what is the limit at infinity and at negative infinity, because there's two ends to a graph, the one on the right and the one on the left, positive infinity and negative infinity, that we can be thinking about. And so the end behavior is just asking you to compute those limits. Okay, so in this function, let's go ahead and find the end behavior. So we'll start by finding the limit as x goes to positive infinity of this function. Okay, so what we'll do is, as we did in the last video, we'll divide through by the highest power of x. In this case, the highest power of x is x cubed. So I'm going to divide through everything by x cubed. Okay, so now we're going to simplify, all right? So x squared goes into x cubed x times, so I can write that like this, 3 over x. X goes into x cubed x squared times. These x cubes cancel. X cubed goes into x cubed once. X goes into x cubed x squared times. And here there's nothing to cancel. Okay, so now we do these limits, right? So as x goes to infinity, this goes to 0. This goes to 0. This stays equal to 4. This goes to 0, and this goes to 0. And so we see that the limit as x goes to infinity is 0 over 4. So the whole thing is 0. Now, that is the end behavior to the right. That's the limit as x goes to positive infinity. Now, what about the limit as x goes to negative infinity? Well, instead of writing this whole expression in here, I'm just going to abbreviate it by g of x because it means the same thing. Right, so we're going to go to negative infinity here. And what happens? Well, I'm going to do exactly the same thing. I divide through by x cubed, and I come to this, right? So this is going to be this. And as I go to negative infinity, these still go to 0. And so the numerator is going to 0, the denominator is approaching 4, and so again, the limit is 0. And so we see that the end behavior is such that to the right-hand side, the function is approaching 0, and on the left-hand side, the function's approaching 0. And we can take a look at that graph. As you can see here, the function, as I go off to the right-hand side, the height of the graph is getting less and less. It's getting closer and closer to 0. So that's the end behavior on the right-hand side. And on the left-hand side, again, the graph is getting closer and closer to the x-axis. So the values of g of x are approaching 0. And that is what we saw analytically. All right, in this example, we've got things a little bit more complicated here. We've got a square root in the denominator. Okay, so we have to be a little bit more careful about how we think about this. We want to compute the limit as x goes to infinity of this expression. Now, as we did before, we asked, what was the highest power of x in the numerator and denominator? Here you have to be a little bit careful. You shouldn't use x squared. You'll see, I invite you to go through the work and try to do it that way, but you see you won't get a meaningful result. Right? I think what you'll get is something like 0 over 0 when you try to evaluate the limit, and that doesn't tell you anything. 0 over 0 is indeterminate. So dividing numerator and denominator by x squared doesn't work. Now, why doesn't it work? Well, if you think about what's happening in the denominator, yeah, we have an x squared, but we also have a square root around it. And so even though there is an x squared in the denominator, the overall behavior of the denominator is more like x, right? Because if I take x squared and then take the square root, that's behaving like x. So we should not divide by x squared here. We should divide everything by x. Okay, so I just wrote multiply by 1 over x here because I want to talk about what to do next with this. And the idea is that you can always pull something under the square root by squaring it, provided that's a positive quantity. Right? It's the same thing on the outside of the square root as it is on the inside if you square it. Now, it is a positive quantity, or at least for our limit, we can assume that it is, because we're letting x go to positive infinity here. So all we care about are very large positive values of x. So we might as well assume x is positive because those are the only ones that have to do with this limit. All right, so we can assume x is a positive number, and so it comes under the square root as, well, 1 over x comes under the square root as a 1 over x squared. So let's go ahead and write that. And while I'm at it, I'm going to cancel these x's here. Now, when this comes under the radical as a 1 over x squared, well, it's going to multiply this times 1 over x squared and this times 1 over x squared. Well, the x squareds cancel here. And then I have a plus 5 over x squared. Okay, so now we can go with our limiting procedure, okay? So this goes to 0. This is just 3 over 1. It's just equal to 3. This is just 4. This term, this little guy here, goes to 0. And so what do I have? In the numerator, I've got 3. And the denominator, I've got the square root of 4. That's 2, right? So it's 3 over 2. So we see that the limit, the end behavior to the right, the limit as x goes to positive infinity, is 3/2. Now, let's do the limit as x approaches negative infinity. And I'm going to get my annoying face out of the way here. When we do this limit, we can go ahead and skip ahead to this step here. Now, we have to be careful about this, and here's why. Well, we're letting x go to negative infinity now. So now x is negative, 1 over x is negative. So I can't just pull it under the square root as a square, right? Because now I will have a negative quantity that I will be turning into a positive quantity if I do that. So that's not allowed. But what I can do is rewrite 1 over x as negative square root of 1 over x squared. Let me write that down and then we'll talk about it. And I'm going to simplify the numerator just like I did down here. So I'm not going to write 3 over 1, I'll just write 3. So in the denominator, we've got negative the square root of 1 over x squared. Okay, so let's just verify that that is indeed true, right? If x is a negative number, right, say it's like -2, right, then this is -1/2, right? Well, if I take the square root of 1 over x squared, I have 1 over 4, the square root of that is +1/2. So to retain the negative, I've got to put a negative on the outside. Right? So if x is negative, when you square it, you've nuked the negative. You no longer have the negative, so we've changed its value. So if I square it and take the square root, I've made it into a positive number. So to retain the fact that it's a negative number, I have to put a negative sign on the outside. Okay, so that's why that's there. And now I can merge these together, but notice that when I do that, I'm going to have a negative sign left over on the outside. Okay, so now we can do the same thing we did before. This stays 3, this goes to 0, this goes to 0. And so what happens? The numerator is going to 3. The denominator is going to negative square root of 4. That's -2. I can just pull that negative sign on the outside. And so we see the end behavior on the left, the limit as x goes to negative infinity, is -3/2. And we can take a look at this in the graph and just verify. Here's a picture of the function. And you can see that as I go off to the right here, the graph is getting closer and closer to being midway between these two lines here. Well, this is height 1, this is height 2. So that's 1.5, that's +3/2. And as I go to the left, you can see that the height of the graph is getting closer and closer to -1.5 or -3/2. So it verifies what we had seen analytically. All right, our third and final example. We want to investigate the end behavior, the limits at infinity and negative infinity of this expression here. Now, this one's a little bit different. We have exponential functions. We don't have polynomial functions, all right? So let's talk about what e to the x looks like, how it behaves, all right? So I happen to have that graphed here. Here's y equals e to the x. And you can see that the graph looks like this. As x goes to infinity, as we go off to the right, you can see this function goes to infinity very rapidly. So the limit as x goes to infinity of e to the x is infinity. Now, what about the limit as x goes to negative infinity? As I go off to the left, this graph descends down to 0. Now, it never actually reaches 0, even though it looks like it's already there, but it's really ever so slightly above 0. This will always be a positive quantity, but yes, in the limit, it approaches 0. So the limit as x approaches negative infinity of e to the x is 0. And so we have that important behavior to keep in mind for an exponential function. Now let's take a look at e to the negative x. E to the negative x is, of course, the mirror image of e to the x. That's what happens when you negate the x in any function. You just get the mirror image across the y-axis. And so it has the opposite behavior. The limit as x goes to positive infinity of e to the negative x is 0. And the limit as x goes to negative infinity of e to the negative x is positive infinity. So let's keep those in mind when we sort out this next problem. Okay, so back to the problem. Investigate the end behavior. Okay, so we're going to take the limit as x goes to infinity of this expression. Okay, so to do this, let's do something similar to what we did before. Last time we divided through by the highest power of x. Well, here we don't have powers of x, we have exponential functions. But I can do the same thing. I will divide through by the exponential function. So that's the same as multiplying the numerator and denominator by e to the minus x. Dividing by e to the x is the same thing as multiplying by e to the negative x. Now, whenever you multiply e to the x times e to the negative x, well, we know that's equal to 1, right? You know that when the bases are the same, you add the exponents, and x plus negative x is 0, and any non-zero number raised to the 0 power is equal to 1. So these cancel. Same with the stuff down here. So with all that stuff gone, I think we can see what the limit is, right? Because of what we observed on the graphs, e to the minus x, when x goes to infinity, we saw that this stuff goes to 0, and same with this. So we have 0 plus 3 over 0 minus 5. So we can see in the limit that this is approaching negative 3/5. Okay, so let's investigate the end behavior on the left. That is the limit as x goes to negative infinity. Okay, so now what we're going to do, we actually don't need to do this step. We can actually compute the limit pretty much right where we are. All right, and the reason is that we observed already that the limit as x goes to negative infinity of e to the x is 0. So we can already see that this limit is 0 and that limit is 0. So I can see just by looking at it here that this limit is going to be 2 over 7. All right, so keep that in mind. I mean, we wanted to do it here because we wanted to get something whose limit was 0. So, e to the x, its limit's not 0, it's infinity, right? So let's multiply by e to the minus x so that we can get things whose limits are 0 so that we can get rid of them. And that allowed us to get to the answer. Here, we started with something whose limit is 0. When x goes to negative infinity, this is already 0, so no work is required. We can simply make that statement and get to the answer right away in a single step. And let's take a look at the graph here of this function. We see that when x goes to positive infinity, as x goes to positive infinity, you can see the height of the graph is approaching. This is actually getting closer and closer to negative 3/5. And as x goes to negative infinity, the height of the graph is not going to 0, it's leveling out right over here. And if you were to measure that carefully, you'd see that that is 2/7, just as we had determined. And so there you go, end behavior of functions, the limits at infinity and minus infinity.